Hey, AP Chemsters, this is Mrs. Vanderlei bringing you another edition of the Blank Wall series. Today we start off in Chapter 12, Solutions. Hopefully you're very familiar with solutions. There are a lot of solutions out there. We talked about a lot of them back in Chapter 4 was the solution stoichiometry. We talked about solutions in Chapter 6 with thermodynamics. We talked about dissolving the copper chloride in water and it got hot, things like that. So this is another section about solutions. We're going to be talking about types of solutions and solubility to start off with. There are many types of solutions. It doesn't have to be a liquid, although the most common form is. Is a solution defined then as it's a homogeneous, meaning similar throughout, mixture of two or more substances in a single phase. That phase can be solids, liquids, or gases. It says it doesn't have to involve liquids. The most common example of gaseous solutions would be our own atmosphere. Here is a solution: nitrogen, oxygen, carbon dioxide, etc. So it's a mixture of different gases. Solder is a solution of lead, tin, etc. They use solder in welding, but it's not just a single element. It's a mixture, a homogeneous mixture of solids together. But again, the most common solution here will be definitely the liquid phase. I think of solution, I think of my iced tea again. So my solution would be the iced tea and the water. So a solute is a component in lesser concentration, the dissolvee, if you will. And that would be my tea or maybe my sugar if I have it sweet tea. The solvent is a component in greater concentration, the dissolver. That would be my water in the case of my iced tea. Please note your definitions, know them very, very well, because later on we'll be doing calculations where it's so important that you know which is a solute and which is a solvent, and you keep them straight. Okay? So we've talked about this before. Intermolecular forces we learned in Chapter 11. And again, why do we have to know this? Because when we talk about solubility, there is a catchphrase that says like dissolves like. What does that mean? Polar molecules tend to dissolve polar and ionic compounds. So the reverse of that be nonpolar molecules dissolve nonpolar compounds. So there's a little joke here. It says, what there's a river and one dissolved completely. It was polar. Ha 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 ha. Anyway, so apparently the rest of them were nonpolar. What makes a polar compound? Remember what we did back in Chapter 11? What are we looking for polar molecules? We're looking for two things: having polar bonds, which I call the big four. So if a bond contains nitrogen, oxygen, fluorine, and chlorine, that would be a polar bond, and it has to be asymmetrical or not symmetrical. And so the case of water being H2O, I can do something like this. Hang on. So if I remember water, here's my oxygen, here's my hydrogen, and here's my hydrogen. Does this criteria for being polar? The answer is yes. It has a polar bond. Here's one of my big four, oxygen with hydrogen. So that bond is polar, and it is not symmetrical. It is not linear. But what about the case of, let's say, a carbon chloride? So here's my carbon, chlorine, 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 and chlorine. That would be first case. I do have polar bonds, but it is perfectly symmetrical. Each bond is 109 degrees apart from each other. So that would be a nonpolar molecule. So make sure you remember it has the big four, which is your nitrogen, oxygen, fluorine, chlorine, and it is not symmetrical. It is a polar molecule. So my carbon tetrachloride over here would be nonpolar, and it would dissolve nonpolar solvent, or excuse me, solutes, because that would be my solvent. So there are things that have to occur for a solution to form. So remember, we have two things. We have the solute and we have the solvent. So the first thing that has to happen is that we need to break apart the attractions of the solute. So we need to break apart the solute to overcome either the intermolecular forces, if it is a covalent solute, like sugar would be, or you break part the ionic interaction. So you have to somehow entice the positive and negative ions to split apart. So that's the first thing we have to do. And then what? We have to do something with the solvent. We have to have reactions between the solute and the solvent. That's why like dissolves like, because the polar molecule will have an interaction, have an attraction with the solute molecules. What about the nonpolar? Well, we still have to have the London dispersion attractions between the nonpolar solute and solvent. Thirdly, the solvent has to do one more thing. The solvent must make room for the solute. It has to form spaces, if you will, for the solute particles to take up. So we're breaking apart the solute, we're attracting, we are attraction, there has to be an attraction between the solute and solvent, and then the solvent has to break up too. So we're going to find out later about this idea of breaking apart and this attraction. And think of it in terms of energy like we did in chapter 6. Okay, go to the back burner. Go ahead and turn the page and see what's up next. So this is a very, very important concept here with our vitamins. Vitamins are classified as water-soluble or fat-soluble. Fats, as you know, are nonpolar. So water-soluble vitamins dissolve in body fluids and can easily be eliminated in the urine, so there's little danger of overconsumption. Fat-soluble vitamins can accumulate in the body's fatty deposits. Over the consumption of fat-soluble vitamins can be dangerous to your health. So examine each structure of each vitamin shown and classify it as a fat-soluble or water-soluble. So I want you to take a little bit of time and look for the two things I told you before. Are there polar bonds? And is that molecule symmetrical or asymmetrical? Once you decide that, go ahead and label them as fat-soluble or water-soluble. So pause this, make your decisions, and come back. Okay, so what about vitamin C? What do you notice here? Oh, I'm noticing OHs, 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 OHs. Here, this is actually called an ether in a sense. We have an O in the middle. Actually, no, it's not. It's actually because of the double bond O. Anyway, so I see a whole bunch of O's. What you know are polar bond or polar four combined with either carbon or hydrogen. So I do have polar bonds. So is this molecule symmetrical or asymmetrical? It looks pretty asymmetrical to me, so I call this water soluble. It's a polar molecule. Okay. What about vitamin K? It looks like K3. I only notice these two oxygens here, and everything else is carbon. So the question is this symmetrical or not? The answer is it is. In a sense, the O's here and the O's here kind of balance each other out. So there is no unequal pull, if you will. And it's a pretty symmetrical molecule. So this would be a fat soluble. So be careful with vitamin K. You don't want to overconsume that. What about vitamin A? What do you notice about that? I see one OH here, and I see a whole bunch of other just carbons. So even though that is a polar bond here, there's a huge area of nonpolar. My nonpolar wins out over my polar, and this again is a nonpolar molecule. Very, very, very slightly polar because of the OH right here. The overall molecule is non-polar, so it's fat soluble as well. So put FS here, fat soluble. And finally, B12, or excuse me, B5, excuse me, I see a lot of O's and H's here. I see O's, I see N's. That's again one of the big four. Here's another OH, here's another OH. I would say it's a pretty polar molecule because I have lots of O's, some N's, and it is not symmetrical. So this would be a water soluble right here, WF, water soluble. So again, got to be really careful with what you consume. Watch out for your vitamin K's and vitamin A's. Let's go ahead and problem number 3, which solvent water, which is H2O, which we know is polar, or hexane. That's C6H14. Does hexane, that's a 14. Does hexane have any oxygens, nitrogens, fluorines? No. So the hexane is nonpolar. So decide what would dissolve in each. So take a few minutes out and decide which solvent would be appropriate for each of the following. NaCl is ionic, so it'd be polar solvent. Ionic is extreme case polar. You have full charges for the partially charged water to be attracted to. So in that case, keep in mind, here's my sodium, my oxygen end of my water will be highly attracted to that. And here's my chlorine, the hydrogen end will be attracted to this. HF is very polar, so again, water. Octane, I see no oxygen, hydrogen, whatever. I'm sorry, oxygens or nitrogen or whatever, so it is not polar, so I pick hexane. And ammonium sulfate is ionic. Once again, I pick water because water dissolves most ionic substances. And then finally, problem number 4, decide whether liquid hexane or liquid methanol. Methanol, OL, has again that OH group. It's not a hydroxide if it's attached to carbon. It's an alcohol. Is more appropriate solvent for grease and potassium iodide. Go ahead and make your choices. Well, hopefully you had hexane here and water here because C20H42 again is not polar. There's not a single big 4 in that. Potassium iodide is ionic. So pick your polar water. To the next page. All right, I alluded to something in section 12.2 about the idea of breaking things up and having that attractions. So we're going to talk about the energies involved now of what's happening here, endo or exo. So if I were to break apart a solute, breaking it up, that involves energy. So this has to absorb the energy to break out. Notice that delta H is positive. Okay, it's positive here. So overcome intermolecular forces. Again, you have to make room for the solute or the solute to expand into the solvent. So you have to overcome this. You need to add energy. Once again, this is endothermic. So over here, allowing the solute solvent interact. So if I have the attractions, two magnets come together, boom. All right, energy is being released. So if you have that idea of attraction, we're talking about positive and negatives attracting each other. Notice it's exothermic, delta H is negative. Okay, so keep that in mind too. So go ahead and look at problem number 5 and answer the question. So I'll pause this. It's going to take a little while to read it and think about it, but this problem is really kind of neat because it's really showing you the idea of breaking things apart, of having the expansion, showing how the solute fits into the spaces. So read this, decide what your answer is, and then I'll come right back. Okay, so hopefully you got it. And what's going on here? This one again is picking it up. You have to absorb energy, so delta H is positive. Here you have to break up the intermolecular attraction between the water molecules or whatever, polar, so it could be water. So again, delta H is positive. And here the two snap together. There's attraction, so that's highly exothermic in most cases. So it's a negative, and that's what letter D is. But do you remember back in the case when we had calcium chloride in water, and then we had ammonium nitrate? The net result was exothermic here. The net result was endothermic here. So why was this exothermic? Because the attraction was more exothermic than the two breakups. Why was this overall positive? Because the snapping together of the attraction was not enough to overcome the endothermic process of breaking everything apart. So that's why this was overall endothermic, but this was overall exothermic, because that last step number 3 in the case of this problem, was not enough to overcome the endothermic process. So whichever one is bigger, so step 1 and 2 is less than 3, we're going to say polynomial, but if step 1 and 2 is greater than 3,